On February 25, 2009, Turkish Airlines Flight 1951 departed from Istanbul Atatürk Airport in Turkey, bound for Amsterdam Schiphol Airport. On board were 128 passengers and 7 crew members. The flight seemed routine, but beneath the surface, technical and human errors were brewing that would lead to a tragic crash. So the flight was particularly significant for the first officer, Murat Sezer, who had only completed 17 flights since joining Turkish Airlines and had never flown to Amsterdam before. Due to his inexperience, he and his captain were joined by a safety pilot, Olgay Ozgo, who sat in the jump seat to assist with the workload and ensure procedures were followed. However, the crew faced an unexpected challenge early in the flight. The captain's radio altimeter, which measures the plane's height above the ground, was malfunctioning. It incorrectly read -8 feet, no matter the actual altitude of the aircraft. While this was an odd issue, it didn't seem critical at the time, because the first officer's altimeter was functioning correctly, and the crew believed they could safely proceed with the flight. As the Boeing 737-800 cruised over Eastern Europe on its way to Amsterdam, nothing seemed amiss. However, as the plane began its final approach into Schiphol Airport, the crew unknowingly faced a ticking time bomb that would soon reveal itself during the critical moments of landing. Before diving into what went wrong, it's essential to understand the importance of the radio altimeter in the final stages of flight. As a plane nears the runway, it needs to execute a maneuver called a flare, in which the nose pitches slightly upward to slow the rate of descent, allowing for a smoother landing. Simultaneously, pilots reduce engine thrust to idle, helping the plane descend at the correct rate. Modern aircraft, like the Boeing 737-800, can automatically handle these actions through the autopilot system. However, the autopilot needs 3 critical pieces of information to initiate the flare correctly. The target altitude on the autopilot panel must indicate that the plane is nearing the runway. The flaps need to be set at a certain angle, indicating the aircraft is in the final stages of landing. The plane must be below a certain height, around 27 feet, according to the radio altimeter, signaling it is very close to the ground. Unfortunately, the captain's malfunctioning altimeter would play a critical role in the upcoming disaster. At approximately 10:25 a.m., as Flight 1951 descended through 8,000 feet over the Netherlands, an audio alert sounded in the cockpit, signaling that the landing gear was not down. The captain immediately recognized this as a false warning, caused by the faulty altimeter reading -8 feet, as if the plane were already on the ground. He pointed this out to the other crew members, and they continued preparing for landing. As the aircraft approached Amsterdam, it had to descend quickly in what is known as a slam dunk approach, intercepting the glide path from above. To achieve this, the first officer, who was flying the plane, selected the vertical speed mode on the autopilot, setting a rapid descent rate of 1,400 feet per minute. This fast descent was not unusual in busy airspace like Amsterdam's, where air traffic controllers often guide aircraft on shorter approaches to save time. However, unbeknownst to the crew, selecting this descent mode met all 3 criteria for the autopilot to enter flare mode prematurely. As a result, the auto-throttle system mistakenly thought the plane was only seconds from touchdown and reduced engine thrust to idle, causing the aircraft to begin slowing down dangerously. With the plane descending too quickly and the autopilot prematurely reducing engine power, the aircraft was now on a collision course with disaster. The speed began to drop rapidly, but the pilots focused on completing their before landing checklist did not notice. At 10:25 a.m., the aircraft intercepted the glide path from above, requiring more thrust to maintain a proper descent. However, because the autopilot believed the plane was just above the runway, it didn't increase thrust. Instead, it raised the nose slightly, trying to maintain the false flare, further worsening the situation by bleeding off even more speed. In the final minute before the crash, the stick shaker, a device designed to warn pilots of an impending stall, activated, alerting the crew that the aircraft was about to lose lift and fall from the sky. The safety pilot urgently called out the falling airspeed, which had dropped to 107 knots, far below the necessary 144 knots required for landing. The first officer immediately pushed the throttles forward and lowered the nose in an attempt to recover. But just then, the captain took control. When the first officer relinquished the controls, the autopilot once again brought the throttles back to idle. The captain then pushed the nose down and advanced the throttles to full power, but by this point the plane was too low to recover. Just 15 seconds after the stall warning, the aircraft slammed into a field 1.5 kilometers short of the runway. The plane broke into 3 pieces upon impact. The crash killed 3 pilots, 1 cabin crew member, and 5 passengers. Remarkably, 117 passengers survived, though many were severely injured. Those who were able to walk immediately exited the wreckage through the open doors and gaping holes in the fuselage, fearing the aircraft might explode. The accident raised questions. How could a modern airliner like the Boeing 737-800 stall so close to landing? And why didn't the pilots notice the problem sooner? The investigation by the Dutch Safety Board revealed that Boeing had been made aware of the potential consequences of a faulty radio altimeter on the autopilot system as far back as 2004. 5 previous incidents involving Boeing 737s erroneously entering flare mode had been reported, but in each case the pilots quickly noticed and took control of the aircraft before anything serious happened. In response, Boeing issued a software fix in 2006 to prevent similar issues. But this fix only applied to aircraft built after that year. The Turkish Airlines 737 involved in the crash had been built in 2002 and was not covered by the update. Boeing didn't consider it a serious safety issue, assuming that pilots could always disable the autothrottle and manually fly the aircraft if such a problem arose. The Dutch Safety Board's report criticized Boeing for not addressing the issue in older aircraft, and it recommended improvements in reporting mechanisms to ensure that manufacturers like Boeing were aware of potential problems before they caused accidents. However, the report also found fault with the pilots for not noticing the impending stall sooner. Further analysis revealed that Boeing pilots, unlike their Airbus counterparts, tended not to monitor the autopilot as closely. Research showed that Boeing cockpits had less intuitive displays for speed and altitude changes, which may have contributed to the pilot's failure to recognize the stall in time. Additionally, the pilots continued their approach even though the landing checklist was not complete and the aircraft did not meet the criteria for a stabilized approach. The investigation concluded that this crash was the result of both pilot error and automation malfunction, an unfortunate combination of factors that led to a deadly outcome. Following the crash, Boeing issued warnings about faulty radio altimeter readings and the potential for autopilot flare mode issues. Turkish Airlines also introduced additional training for pilots on how to handle low-altitude stalls. The final report recommended that these procedures become a standard part of all airline pilot training. In 2020, a New York Times investigation alleged that Boeing had downplayed its role in the crash and influenced the Dutch Safety Board to focus more on pilot error than on the autopilot flaw. Although the Dutch Safety Board denied this, the accusations cast a shadow over Boeing's involvement in the incident. Today, the lessons from Turkish Airlines Flight 1951 serve as a reminder of the delicate balance between technology and human oversight. As aviation becomes more automated, it's essential that pilots remain vigilant and maintain control, especially when the unexpected happens.